Let's work on complex roots of characteristic equation IVP problems. So our first problem is y double prime plus 4y equals to 0, y0 equals to 0, y prime of 0 equals to 1, and what happens as t approaches to infinity. Now, the first thing we want to do is, since we have this second order differential equation, we want to put the characteristic equation, put this in the characteristic equation form. So we would have r squared plus 4 equals to 0. Now, if we try to solve this differential equation from algebra, we can say that r squared equals to negative 4. Therefore, r is going to be plus or minus 2i. So this will be our solutions for the differential, for the roots. These are our roots, and to build our solutions from these roots, since we have complex roots, we're going to use this formula: e to the at c1 cosine of bt plus c2 sine of bt, where a is and where r is in terms of a plus bi. This is the imaginary part, and this is the real part, a. So we will build this solution for y. So y will be equal to e to the 0t c1 cosine of 2t plus c2 sine of 2t. Okay, now e to the 0t is just 1, so our solution will be y equals to c1 cosine of 2t plus c2 sine of 2t. Okay, now we can make use of these initial conditions to solve this differential equation for a particular solution. And let's plug 0 for y0 to see what happens. So y0 will be c1 times cosine of 0. Cosine of 0 is 1, so I'm just going to erase that. Plus sine of 0 will be 0, so we will not add anything. So c1 plus 0, which is c1. And c1 is equal to 0. This means that we do not have a cosine term in our solution. So we can write this solution as just c2 sine of 2t, since c1 is 0. Now we are given one more initial condition. Since we have two constant terms, one initial condition is not good enough to solve this differential equation. So we want to know another initial condition, and this is y prime of 0 equals to 1. So we are going to take the first derivative, and since I know that c1 is 0, I'm not going to bother taking the derivative of this part because it's just going to waste your time. So anytime you get one value for any part, just update your solution. Okay, I just updated my solution. I was here, I went here, I got c1 equals to 0, and then I went to this part to update my solution. Now let's find what y prime is. Y prime of t, y prime equals to, the derivative of sine is cosine, the derivative inside is 2, so we're gonna have 2 cosine of 2t multiplied with c2. Okay, and y prime of 0 will be cosine of 0 is 1, so we're gonna have 2 times c2. That's equal to 1, so c2 is 1 over 2. So our solution will be our solution, remember, was y equals to c2 sine of 2t, so we will have y equals to 1/2 sine of 2t. Okay, and what happens as t approaches to infinity? Well, sine is a function that keeps oscillating, right? We start from 0, and we will oscillate between 1 and 0. Okay, but we will have a 1/2, so it doesn't matter. As t approaches to infinity, sine of 2t just oscillates. And since sine doesn't matter if the domain is 2t, okay, we'll bound between 1, -1, and 0, 1, okay, inclusive. So since we're multiplying this with 1/2, oscillates between it will be negative 1/2 and 1/2. So it will be negative 1/2 comma 1/2 inclusive. Now let's work on this example problem. Y double prime equals y double prime plus y equals to 0. This initial condition and this initial condition is given, and what happens as t approaches to infinity. This is the same type of problem. We're going to start with creating the characteristic equation, since this is a second order homogeneous differential equation. So guys, anytime you see a second order differential equation and it's homogeneous, you need to find the characteristic equation. And as you can remember, we either have equal real roots, uh, distinct real roots, or complex real roots. And over here we have r squared plus 1 equals to 0. Obviously r is going to be plus or minus I to create this equation, satisfy this equation. So we have complex roots again, and our solution, as I showed before, is e to the at plus multiply with c1 cosine of bt plus c2 sine of bt. Well, our real constant doesn't exist, it's 0, so our solution will be c1 cosine of t, because the constant is just going to be 1, plus c2 sine of t, and this will be equal to y. Now let's plug these initial conditions to see what happens. So the first initial condition is y of pi over 3 equals to 2. So y of pi over 3 will be c1 cosine of pi over 3 plus c2 sine of pi over 3, and this is given that it's equal to 2. So cosine of pi over 3 will be what? Pi over 3 is 60 degrees, so cosine of pi over 3 will be 1/2, and sine of pi over 3 will be root 3 over 2, right? Remember, if you are struggling with this, you can draw this triangle, okay, 30, 60, 90 triangle. Okay, this will be 1, this will be 2, and this will be root 3 from the properties of this triangle. So if you have this cosine of 60 degrees, which we have right now, we will get the adjacent side and the hypotenuse, and for sine we will get the opposite divided by the hypotenuse. So it's better to memorize these, but you can just memorize like some of these classic triangles, like 45, 45, 90. This is also useful. 1 root 2, I'm sorry, 1 root 2. And yeah, these are the main ones you can memorize. These are usually pretty useful to get most of these sine, cosine, tangent values. So anyways, we will have c1 over 2 plus root 3 over 2 c2 equals to 2. Now we will not be able to solve this equation because we have two unknowns, but if we use this initial condition, y prime of pi over 3 equals -4, we will be able to have two equations with two unknowns, and this will help us solve for both of these values. So let's do it. Let's get y prime of t. Since we don't know anything about c1 or c2, we cannot update this solution, so we will have the derivative eventually. So the derivative, the first part will be negative c1 sine of t. Guys, a lot of you may ask, when you're taking the derivative, should we multiply with this constant? Doesn't that just gets inside c1? The answer is no, because here's the thing, guys. I understand where you're coming from. I understand it makes sense for you to get rid of that. But no, because we are dealing with simultaneous equations over here. So C1 and C2 are treated as a variable instead of a constant. I mean, it is a constant differential equations wise, but when you're thinking about the we have many multiple equations, we need to use these constants to solve for c1 and c2. So guys, don't make this mistake. Don't try to put this -1 inside c1, or if you have a constant number, sometimes we get that just like we got it on the previous question. Don't get it inside c1, okay? And this derivative will be c2 cosine of t equals to y. Now let's find y, oh, this was y prime, my bad, y prime. So now let's find y prime of pi over 3. Y prime of pi over 3 is going to be negative c1 times sine of pi over 3 was root 3 over 2 plus c2 times 1 over 2. 1 over 2 is going to be equal to negative 4. Negative 4. So our two equations is c2 over 2 minus c1 times root 3 over 2 equals to negative 4. And the other equation is this equation right here. Okay? Awesome. Now we have these both equations. What we can do about these is instinctively I just want to multiply everything by 2 so we can make these equations look much better. So we're gonna have c2 minus c1 to the c1 multiplied with root 3 equals to negative 8, and c1 plus root 3 c2 equals to 4. Okay. Now, what do we want to do here? Let's multiply the second equation with root 3. Okay, we will have c1 root 3 plus 3c2 equals to 4 root 3, right? And now we can add this equation to the first equation because we have this c1 root 3 term. This will cancel out. So when we add these, we will have c2 plus 3c2 equals to negative 8 plus 4 root 3. So 4c2 is going to be negative 8 plus 4 root 3. So c2 will be negative 2 plus root 3. Okay. And c1 from any of the equations, now you are able to find what c1 is. So I'm going to use this equation, c1 plus 3 root 3 c2. So c1 plus root 3 times c2 will be negative 2 root 3 plus 3 equals to 4. So c1 minus 2 root 3 equals to 1. I'm just sending this 3 to the right hand side. So c1 is going to be 1 plus 2 root 3. Okay? And we know what c2 is. We know what c1 is. So now we can just rewrite the first equation for y to solve this differential equation. So our equation for y was c1 cosine of t plus c2 sine of t. So we will have 1 plus 2 root 3 cosine of t plus c2 sine of t. And this will be our particular solution for this differential equation. Now let's work on another homogeneous differential equation problem. We will start by getting the characteristic equation, since we have a second order differential equation. So we will have r squared minus 2r plus 5 equal to 0. Since the b squared minus 4ac will generate a negative delta, we will have a complex root here. So let's find what the root is. So using the quadratic formula, I will get negative b, which is 2, plus or minus square root of b squared is 4, minus 4 times 5 times 1. So we will have negative 16 here. So this will eventually correspond to 4i. So 2 plus or minus 4i divided by, and RA is 1, so we will have 2. So our solutions are just like this, okay? These are the roots. Now that we have the roots, we can just build the differential equation from the formula e to the real part, e to the t, times c1 cosine of the non-real part, 2t, plus c2 sine of the non-real part 2t. Okay, we have this the solution, and now we can just plug the initial values to get c1 and c2. So we are given y of pi over 2, which is actually a very good one. E to the pi over 2 times c1, but pi over 2 times cosine of 2t will be a cosine of pi, plus c2 sine, and pi over 2 times 2t is pi also, equals to y. So this is just going to be 0 because sine of pi is 0, and this is negative 1, so we will have negative c1 inside the parentheses. So e to the pi over 2, negative e to the pi over 2 c1 equals to, I'm sorry, this is not going to be y, this is going to be the value we are given. Let's just fix that. We are given 0. Okay, we are given 0. So we have an exponential function, but there's no way we could get this exponential function to be 0 because our base is e. Any exponent of a number, a non-zero number, will generate even number. So the only way to make this equation satisfactory is to make c1 equal to 0. So from here, we can draw this conclusion that c1 must be equal to 0. Okay, so since c1 is equal to 0, our differential equation can be updated to y equals to c2 e to the t sine of 2t. Okay, I just send this e to the t inside this one, and since c1 is 0, we can just ignore this term. So this is now the updated version of our differential equation, and y prime of pi over 2 equals to 2. So taking the first derivative, we need to take the first derivative of this one. So we'll have c2 e to the t from product rule sine of 2t plus 2 cosine of 2t multiplied with e to the t times c2. This is the first derivative, and we are given y prime of pi over 2 was equal to, what was it equal to? 2. Okay? This is equal to 2. So we're gonna write pi over 2 here. Since pi over 2 for this one will be sine of pi, we can just ignore this one, this first term, because it will be 0, right? Sine of pi equals to 0. So we will only write this over here. So let's just do it. c2 e to the pi over 2 sine of pi plus 2 cosine of pi times e to the pi over 2 times c2. Okay, now sine of pi is 0. That's what I was trying to say a little bit while ago, and we only have this term. Now cosine of pi is negative 1, so we will have negative 2c2 e to the pi over 2 equals to not y, it is equal to 2. Okay, so we can now solve for c2. We can divide both sides with negative 2, and we will have c2 e to the pi over 2 equals to negative 1. And now we can solve for c2, and c2 will be negative 1 over e to the pi over 2. So now that we know what c2 is, we can just go ahead and plug this into our differential equation. So our c2 was negative 1 over e to the pi over 2, and our the differential equation is e to the t sine of 2t. So we will have multiplied with e to the t sine of 2t equals to y. Now, what happens as t approaches to infinity? Well, first of all, this sine of 2t is a function that is going to go between negative 1 and 1. It's going to oscillate between this. And we have an e to the t function, which will affect the magnitude of this function because we only have one exponential term here. So this will make the magnitude approach infinity. This negative 1 term would make this approach negative infinity. However, since sine is oscillating between negative 1 and 1, this negative and negative could be positive. So our solutions will sometimes approach the positive infinity and sometimes approach the negative infinity. So the best way to answer this question is, as t approaches to infinity, y approaches to y, the magnitude, the absolute value of y approaches to infinity. And this sine, always guys, trig functions, the sine and cosine more specifically, cause an oscillation. So you will keep oscillating because these are periodic functions, okay? Periodic functions. So, and it oscillates, okay?